Hello, everyone. The title of my talk is Online Pricing with Reserve Price Constraint for Personal Data Markets. In this talk, I will cover problem formulation, fundamental design under linear market value model with uncertainty, extensions to nonlinear models and other similar applications. I will also report evaluation results and summarize the contributions. Nowadays, massive data are collected to seamlessly monitor human activities, for example, product ratings, electrical usages, social media data, health records, and locations. However, for the sake of security, privacy, or business competition, most of data owners are reluctant to share their private data, resulting in a large number of data islands. The data isolation status locks the value of personal data against potential data consumers, for example, commercial companies, medical practitioners, and researchers. To promote personal data circulation, many data brokers, such as Factual, DataCo, and DataSift, emerge as bridges between the data owners and the data consumers. We call the data circulation ecosystem data market. First, the data broker collects personal data from the data owners. Then, the data consumers sequentially come to the market. In a certain round, a data consumer makes a customized query over the collected data set. In general, the query comprises a data analysis method and a level of noise perturbation. The noise perturbation can not only allow the data consumer to control the accuracy of data analysis, but also can protect the privacy of data owners. Depending on the query and the underlying data set, the data broker can quantify the privacy leakage of all the data owners, and needs to compensate them if a deal occurs. The data broker then posts a price to the data consumer. If the price is accepted, the data broker will return the noisy answer, and compensate the data owners as planned. Otherwise, this deal is aborted, and the data consumer goes away. In this work, we consider how the data broker can maximize the cumulative revenue, which is defined as the difference between the payments charged from the data consumers and the privacy compensations allocated to the data owners. Ideally, for the query Qt in round T, the data broker should post the price Pt, which takes the larger value of the total privacy compensation Qt, and the market value Vt. Here, the total privacy compensation works as the reserve price of the query. In fact, the reserve price is virtually determined given the query, while the market value is unknown, thus generating regret RT at the data broker. Now, the revenue maximization problem is converted to minimizing the cumulative regret. We examine the regret function in round T. If the reserve price is higher than the market value, the posted price must be higher than the market value. The query definitely cannot be sold, generating no revenue and no regret. If the reserve price is no more than the market value, a slight underestimation of the market value incurs a low regret, while a slight overestimation causes no deal, generating a high regret. The key of regret minimization is to well estimate the market value of each query. To build the market value model, we adopt a key principle from contextual pricing in computational economics, which states that the market value of a product is a function of its features. Here, we let xt denote an n-dimensional feature vector of the query Qt. The function f can be linear or nonlinear. To make the pricing model more robust, we allow some uncertainty delta t in the market value, which is independent of the feature vector. We next identify the features for measuring a query's market value. One trivial way is to directly encode the contents of the query. However, the data analysis method is hard to embody the economic value. We turn to using the valuations of the data owners about the query, namely, the privacy compensations, as the feature vector. First, such a feature representation inherits the principle of cost plus pricing, which has been widely used in personal data pricing. The cost is the total privacy compensation, or the reserve price. Second, the privacy compensations can be observed by the data broker, and help the data broker to discriminate the economic values of different queries. For example, if the privacy compensations are higher, which implies that the privacy leakages of the data owners are larger, the knowledge discovered by the data consumer is richer, and the market value of the query should be higher. Third, considering the large scale of the data owners, we can perform feature reduction by PCA or aggregation or clustering. Let's get into the fundamental design under linear market value model. The market value Vt is the dot product of the feature vector xt and an unknown weight vector theta star. The data broker needs to online exploit and explore the weight vector. We also let kt denote the data broker's knowledge set of the weight vector in round t. We start with one-dimensional case. For example, the single feature is the reserve price, and the weight denotes some revenue to cost ratio. In addition, the knowledge set is an interval, based on which the data broker can easily compute a lower bound and an upper bound on estimating the market value. Moreover, in a certain round, according to the binary feedback that a posted price is rejected or accepted, the data broker can learn whether the market value is higher than the posted price or not, thus refining its knowledge set. If the data broker posts the larger value of the reserve price and the lower bound, the query can be sold with the highest probability. However, in the worst case, the data broker cannot refine the knowledge set, and thus cannot benefit the following rounds. We call such a price a conservative posted price. If the data broker posts the large value of the reserve price and the middle price, it suffers a higher risk of losing the current revenue, compared with the conservative price. However, in the worst case, the data broker can narrow down the knowledge set by most, thus benefiting the following rounds most. We call such a price an explorative posted price. In fact, these two types of posted prices give different biases to the immediate reward and the future reward. Now, the question is when the data broker should post which price. Our strategy is to measure the size of the knowledge set, for example, the width of interval in the one-dimensional case, and set a threshold. If it exceeds the threshold, the explorative price is posted to further refine the knowledge set, otherwise, the knowledge set is near optimal, and the conservative price is posted. We further consider the multi-dimensional case. The holistic process is the same as the one-dimensional case. The difference is the format of the knowledge set kt, which now contains a set of linear inequalities and expands with the round number t. Thus, kt can be viewed as a polytope in geometry. In addition, computing two bounds on estimating the market value needs to solve two linear programs, which is computationally infeasible in online mode. To reduce online latency, we propose an ellipsoid-based design. The key idea is to replace the polytope kt with its Lonergan ellipsoid et. In algebra, the ellipsoid can be convenient to be represented by a center vector and a shape matrix. The tasks of estimating the scope of the market value and updating the knowledge set now require only a few matrix vector and vector-vector multiplications. We next show how to incorporate uncertainty. We assume that the distribution of uncertainty is subGaussian. Thus, we can bound the uncertainty in each round by some constant delta. We regard delta as a buffer in posting the price and updating the knowledge set, thus circumventing uncertainty. We show the performance of our proposed pricing mechanism. The single round time and space complexities of the data broker are both square to the dimension of the feature vector n. The worst case cumulative regret, under low uncertainty, is square to n, and logarithmic to the total number of rounds t. Let's look at some extensions. First, we can easily extend to support log-log, log-linear, logistic, and kernelized, nonlinear models. Second, we can also support trading other similar products, which share customization, existence of reserve price, and timeliness, with the queries in personal data markets. For example, hospitality service on booking platforms, online advertising on web publishers, and loan application from banks. We now show the evaluation results. We first investigate the pricing of noisy linear query. We take Movi Elan's 20M dataset, and the linear market value model. As shown in the left figure, when the round number is small, our pricing mechanism with reserve price incurs a regret ratio much lower than that without reserve price. We can find that the reserve price can mitigate the cold start problem in a posted price mechanism, thus reducing the cumulative regret, as shown in the right figure. We can also see from the left figure that, at the end of 100,000 rounds, the regret ratio of our pricing mechanism is lower than 10%. We next investigate the pricing of accommodation rental, under the log linear model, using Airbnb listings in US major cities. The main results are shown in the left figure. We also investigate the pricing of impression in advertising, under the logistic model, using Avazu mobile ad click dataset. The major results are shown in the right figure. We can see from the left figure that, as the reserve price approaches the market value, its impact on mitigating cold start is more evident. We can also see from two figures that, our extended pricing mechanism incurs low regret ratios, for nonlinear market value models, and other similar applications. We report the practical overhead on a Broadwell e-workstation. We can find that, our pricing mechanism is quite efficient to be deployed online. The online latency of 3 applications per round is each in the magnitude of millisecond. The memory overhead is each less than 160 megabytes. Finally, let's conclude the talk. We studied how to maximize the data broker's cumulative revenue in online personal data markets. We proposed a contextual dynamic pricing mechanism with the reserve price constraint to exploit and explore the market values of the customized queries launched by sequential data consumers. The proposed pricing mechanism features the properties of ellipsoid for effective and efficient online optimization. It also supports both linear and nonlinear market value models with uncertainty. We instantiated with the pricings of noisy linear query, accommodation rental, and impression in advertising. We extensively evaluated over 3 practical data sets, and demonstrated low practical regret and online latency, as well as the functionality of reserve price. Thank you for watching. Comments and questions are welcome.